Right now, only a handful of companies in the entire world can train frontier AI models, LLMs. We have Meta, OpenAI, Anthropic, and Google. And it's not like they're doing something different from what we're doing. And it's not like there are new algorithms that they're coming up with that they're using to train their models that's why they're able to do it. They're able to train frontier models while no one else can is because training $1 billion or trillion parameter model costs a lot of money. It costs millions of dollars. And it's not even the compute that actually costs a lot of the money. It's a lot of the times just waiting. We're waiting for nodes in the compute itself to talk to each other, the gradients to move from one to another, and actually go through the distributed training process. But what if we could change that? What if we could cut the communication cost of these trainings down so that training frontier models is accessible to everyone? Hello everyone, my name is Bhavesh. I'm currently a researcher at Nous Research. For those that don't know, Nous Research works on open source and accessible decentralized AI. I'm also a student here. I'm currently an applied mathematics master's student, and I also did my undergrad in CS here. And today I'd like to talk about my new paper, Curva Dion, which tackles that specific issue. But before we jump into that, I'd like to kind of look under the hood and understand how exactly we train LLMs and big models today. For the most part, training LLMs have two major requirements, which make it inaccessible to most people. First of which is the training data. It takes trillions of tokens to train one big LLM. And obviously, those trillions of tokens take quite a bit of time to parse through in a single GPU. So, and another issue is the model size. We want to scale our models to be as big as possible. Scaling laws are what made LLM today possible. So the first key way that we solve the training data issue is through something called DDP, distributed data parallelization. This is a very simple concept, and this is what most industry researchers do right now. We split the data. We shard it between all of our GPUs, and we give all of our GPUs the full model as well. And then we train one epoch on all of these models, combine all of this together, and we consider that as one full epoch amongst all of our GPUs. That way we can scale the number of GPUs we possibly have and train with all of them and put all of our data across all of these GPUs as well. And this is beautiful because this is essentially mini batch SGD. We do that on a single GPU anyway, but now we have scalable number of GPUs. We can expand how big of a network we can train and how much data we can train. The main issue here is each GPU has to have that much data capacity to be able to train that big of a model. For example, here you can see the parameters take P, the gradients take P, and the optimizers take 2P. So we are limited by 2P billions of parameters of data per GPU. That means if we want to scale to anything beyond 100 billion parameters, we kind of need to figure out a way to get past that GPU issue and have the full models be able to train and scale. So our current issue and our current solution, and this is what your GPT-3, GPT-4, and many of the models are trained on, is called FSDP. And the idea is like DDP, but we go and shard everything. This includes the model parameters, this includes the gradients, and this includes the model, the training data itself. And so now instead of 4P of data per GPU, we've cut the problem down by n, which is the number of GPUs that we have. We've transferred our problem of scaling and creating bigger and bigger LLMs by GPUs. So now at every single step, we can all gather and get all of the GPUs together to create one full network, and then we can compute, and then we can free up and move our model in that specific way. Does that make sense to everyone? So here's where we're at right now. We have DDP and we have FSDP. And they're both able to do something that is very beautiful in the sense that they're able to track fast communication, but have a memory constraint in DDP. That makes sense. As for FSDP, we have a memory efficiency issue, where it takes less amount of memory to train the full parameters and all of the parameters in an LLM, but fundamentally, this is limited by your bandwidth and how much you're able to transfer from one GPU to another GPU and concise all of this data together, gather all of this data together. So our main question here is, can we improve this? And what a lot of people have found out is we can, but we'd have to dive one layer deeper and kind of move into optimization, and optimizers specifically. So let's start with the king of all optimizers right now, Atom W. Atom came out in 2014, and from 2014 at 2017, Atom W was released, and till 2024, this was the king of all optimizers. This was able to train any model, and it does actually train GPT-5 and all of the models right now. And the beauty behind why this was able to do it was because it was able to put two separate pieces of information into our gradient descent itself. That specifically is the momentum and the variance as well. So the idea here is fairly simple. With Atom, we can figure out the exact learning rate per parameter, which we need to move to the local minima the fastest way. And this is based on kind of the curvature, mostly that V of t term there. Essentially, if we have something that is steeper, we would take smaller steps. That way we don't have to move as much and we don't jump out of a lot of these local minimas. As for something that has a flatter minima, we're able to take bigger steps. Because if you look at that term, when we have small gradients, flatter minima, you have a smaller V of t. That means that we can do a lot of this parameter-wise, and we can speed things up that way. Does that make sense to everyone? That was pretty cool. And for the longest time, for most people, optimizers seemed like a solved problem with Atom W. Because why wouldn't it be? We can find the optimal minima, and we can do that efficiently. But in 2024, we had a new group of people from an open source company called Moonshot come up with this idea and describe this ill conditioning problem. Where essentially, once we have this concept of Atom, where we're able to take all of the parameters and set a learning rate based on that specific parameter, we run into this ill conditioning problem, where if we start from the same initialization, a lot of these parameters kind of fall into the same minima. If we go back to the ball rolling down a hill, if we start the initialization, it kind of falls into the same minima regardless of where it is. And this happens because we've done parameter-wise optimization. But we forgot that weights are inherently structured as a matrices. So we want something where we have every single neuron, where these balls, learning a different feature. But what we have with Atom is all of these neurons kind of fall into similar minima, so they're learning pretty much the same features from one another. This is why we're able to scale so far and gain good effects. But essentially, we have an ill-conditioned matrix that is pretty redundant. There are multiple neurons doing pretty much the same thing. More rigorously, this is why we actually have that ill-conditioned matrix problem. Essentially, you have this V of t, which is the variance. And what it does is it amplifies the directions, which are very large, and it makes all the directions that are very small go down to 0. So at the end of the day, you have a very low rank matrices, and you only represent a couple of directions. Yes?
Wait, can you quickly explain what low rank matrix means? I hear it a lot, but I'm not quite sure of the actual definition.
Exactly what I just said. So if you have a matrix of our weights, and each of our weights represent some specific direction, if we do a row reduce operation, we see that a lot of these different weights were basically doing the same exact thing. Does that make sense? So we can reduce the full rank of that matrix to be a very low rank. Does that make sense?
Yeah.
We can reduce that matrices to only show up as the first two layers are the only ones that represent features, and everything else beyond that are representing pretty much the same thing. Does that make sense?
Yeah, so it just encodes like less information than it.
Yes, it's redundant. It doesn't encode less information. You have a lot of neurons doing pretty much the same thing, because you lose the structure of the weight matrices being a matrices itself. Does that make sense to everyone? So we have this ill conditioning problem. And from this ill conditioning problem, we've come to the new state of the art, which is called muon. And essentially the idea is we want to take all of the good parts from atom, which is the momentum, and we kind of want to have this one OFT, or the orthonormalized step, where all we're doing is we're setting this condition number to be exactly 1 at every single step. This way we don't have that ill conditioning problem. We're able to make sure that all of our neurons are able to learn as many directions as possible. Does that make sense to everyone? We're able to make sure that our neurons aren't redundant for most part. And that is what Kimi K2 and the people who created muon were able to utilize to create a smaller model with less people and still have this be state of the art. And that blew the entire optimizers industry wide open. Because now you have new models, you have new ways of doing this thing, and new optimizers popping up every single day in order to optimize this specific way of optimization and training our LLMs. We're able to scale this into bigger and more representative machines. And the most prominent one, and the current state of the art in efficiency scalability is called Dion. This is essentially muon, but muon has this issue where every single step we're taking the full weight matrices, and we're orthonormalizing that at every single step. So like we discussed about what FSDP was, you actually cannot do that on muon. But we can create a more efficient way of doing the same exact thing as muon, which lets us to do FSDP as well, which lets us shard all of our model parameters across all of these different GPUs. And now we can train bigger models with less compute. And that's exactly what muon does. More rigorously, that specific thing came from this power iteration sense, where we take our original momentum matrices and we turn it into a lower rank matrices to begin with. Does that make sense? And we make it just low enough where we're still able to represent more features than Atom, and we're able to now transfer that low rank matrices between different networks and between different model parameters. Here's where things get good and where we kind of move into what I'm currently doing. We still have Dion, and we can see how it specifically works, where it's able to take every single step, put it into some low-ish ranked matrices, and then it's able to train across all specific GPUs and whatever compute we have. It's able to do FSDP. But in doing FSDP, we are syncing at every single step. What we do is we compute, we get the gradients per GPU, and then we communicate that at every single step. And that is the next bottleneck of Dion, where we have this syncing issue now, where we're waiting for GPUs to just transfer this gigabytes and terabytes of gradient information between each other. just so we can move on to do the next compute step. Every hour you spend on the GPU costs people a lot. It's like a lot of money. And every hour you're not doing compute means that that money was pretty much wasted.
Just a stupid question, but how much money are we like talking about? Do you like have like a general like sense of like how much money is wasted?
On compute?
Yeah.
I'll get to that.
Okay.
Yes. So we have our key question. Do we really need to sync at every single step? Or can we come up with a way to figure out which steps really make things, which steps we really need to sync at and which steps we really don't? We have the key intuition that, hey, maybe we don't need to sync at every single step. Maybe we need to find the exact steps where divergence would happen if we did not sync. And we can go ahead and only sync at those specific steps. The concept of not syncing at every single step is not new. In fact, there has been a paper that came out in 2024, right after Muon came out, which has an idea of using this variance term to figure out why and when we need to sync. But the issue is that this paper didn't really take off because someone realized that the gradients itself, or the variance itself, is very noisy. So this was causing more synchronization steps than we actually needed to. This is a bad metric for figuring out when we need to sync and when we don't need to sync. But what is a better metric? How can we figure out at which point we need to sync and which point we don't need to sync? So a bit of intuition on why we're going to use curvature to figure that out. The idea here is simple. Let's go back to that bunch of balls rolling down a hill example, right? If you have a bunch of balls rolling down a hill and you're trying to find a minima, the only point at which divergence happens is when one of these balls, or GPUs that is doing this stuff, falls into a very deep hole. Something that has very high curvature. And this is a very known and established fact that this is exactly what causes divergence. You can see that when you have higher curvatures, similar distances are very hard to find the midpoint between. Versus a very flat curvature is basically aligned. If I can see you, I can converge with you. Does that make sense? So we work towards finding a metric. We call it RMMC. And it's essentially the momentum, the norms of the momentum between the previous step and this step, subtracted with themselves and divided by and normalized, essentially. And we can prove that this is an approximate enough estimation for the curvature itself. Boom. That's your problem. And so we ran this on many different models, including GPT and different styles of LLMs, ranging from 160 million parameters to 350 million parameters to 1.3 billion parameters and 3 billion parameters. And we can prove that it only takes 1% of those things to actually make training happen. That's all we really need. That's a 99% communication reduction just between our training. For reference, that is ZR. And that is a straight line because obviously we're training and exchanging data at every single step. And this is a 160 million parameter model. No one uses 160 million parameter models. Right now, GPT is a trillion parameters. But this is a good scale to see what happens between that and a cell sync that uses a very high threshold with very little variance perplexity loss. You can use 3.6 GB instead of 300 GB to pretty much get the same exact effect. We just need to sync whenever there's high curvature.
So you mentioned like a performance loss. How much is it like negligible to the point of like you can ignore it basically, or?
It's negligible to the point of 3 billion parameters, 3 billion parameter models. We haven't tested anything beyond that,
Mhm.
but for 3 billion parameter models, it's negligible that it does not matter. And people are willing to exchange that for this much save.
I'm assuming it scales though, right? Are you like, is there a trend that you've noticed as you go up in parameters? Like, do you assume also that once you get to like the trillion parameters, you also have negligible?
The assumption is that it scales, and that's kind of the baseline of how we deliver a baseline. If we can run a 3 billion parameter model for 100 billion tokens and still lose very little, we're pretty golden. Yes?
Does it affect the accuracy of the scheme if you select for well, if you select the scheme only when the moment will have that that divergence in curvature?
So that's the validation perplexity. No, it's very negligible. Yes?
So what are the different like tau numbers?
Those are the thresholds. So with Curva Dion, you essentially have a threshold that you set, which goes, okay, at what point of these RMMC values do we want to make this synchronization happen? And this is a hyperparameter that we kind of tune. And if you do like a sensitivity analysis of this, we can see that it's pretty much a flat line. So no matter how big of RMMC value you choose between 0.1 to 0.9, it's very negligible and they're all pretty much in one straight line. Does that make sense? Do we have any other questions? Yes?
Yeah, you talked about muons earlier, but I guess like when you say, I get that like you know, you keep redundancy, when you minimize redundancy, right? But I guess when you talk about like with muon, like it keeps the structure of your weight matrices, why is that actually beneficial if the structure of your overall neural network is captured by your backprop? Is it because like your like the directions along which they're creating updates is being like you like consider that with respect to the actual size of like the spaces that you project between with the matrix? Like what is the intuition there, I guess, is what I'm asking. Like why does it matter that muon is like considering the full weight matrix with dimensionality?
So that specifically is this condition number, right here, yeah. So this condition number is based off the singular values of the weight matrices. Essentially, we're trying to figure out and look at weight matrices as a whole. And when we look at it as a whole, we can figure out exactly how many of those layers or neurons are kind of redundant within each other. In Atom, we're not able to do that because we take every parameter and we just figure out the exact learning rate that would be the most optimal for it, and then we optimize for that direction. And because we're not looking at it as a full weight matrices, a lot of these neurons in the same layer have pretty much the same thing as other layers. But now that we look at it as a weight matrices, we can figure out, hey, a lot of these things have pretty much the same thing. And that's essentially the breakthrough moment for muon. And
like,
they're able to do this, yeah.
So you're like encouraging like feature diversity, basically, like.
That's exactly it, yes.
Okay. Is that more helpful at larger models or than smaller models? Like, is there a trade-off? Because muon has more overhead, right? So is it like better to train like Kimi K2 with it than like train like your like 1,000 by 1,000 like fully connected? Like, does it matter? So
Kimi K1 actually came out and was much smaller than a lot of the models that it beat. And that was the proof of concept for muon, where it was able to say that, hey, we don't need as many like variables and parameters as you guys that are doing big models like Gemini, but we can perform as well with this. This is what's going on. In fact, muon itself is a study of its own on understanding why muon is able to do a lot better. It's still an open research topic. So I don't think we have an exact answer of why orthonormalizing it and having that specific way of doing things and that condition number matter so much. It's back to like the neural network problem where we don't really know what the implicit bias going into this optimizer is, which makes it kind of better.
And is K-means like mixture of experts? Like, do they train with MOE layers, or I guess like, do you use neuron with MOE, or because they're both pretty recent, right? Like I'm not like up to date at all.
So optimizers, it doesn't matter if it's MOE or not. You
but
can
have they like trained it with an MOE and show that like
Yes.
because MOE the idea is you can capture more features as well, right? So is it like it amplifies each other, or is it like?
I'm not sure if Kimi K2 is MOE, but I'm 100% sure that Muon has done tests on MOE
Okay.
and it works.
That's pretty cool.
Yeah.
So, it looks like a lot of these prior methods like Atom, Eon, even the earlier iteration of Eon, it looks like a lot of those methods that were improvements came from numerical learning algebra, but it looks like what you're doing is something that's very different, right? You're not working on linear algebra, you're looking directly at the scheme itself, and you're saying, when this happens, right, when this curvature is too far, right, then don't sync, right? Don't waste your computational resources, right?
Yeah.
Do you anticipate any more methods coming from this sort of numerical direction, sort of scheme direction?
I actually disagree with your take on the numerical idea. Essentially, with Atom and the reason why it was better than SGD to begin with was because SGD just had the initial gradient. And it was only able to capture the first derivative of information. The reason why Atom was able to beat it was because Atom was able to capture momentum and variance, which you can think in a sense is some form of second derivative and some approximation of it. And in that similar vein, I'm also able to capture the trace or the curvature, which again is like a third derivative or second derivative kind of an idea. The idea is if we can pack more information on what exactly they're minimizing in that optimizer, we're able to do more and more efficient things because we know more. It's like being blinded and only able to see through blinders to actually having a bigger and bigger peripheral vision as you're walking down the lost landscape. That's kind of the idea of that's kind of the motivation of how I went about it. How can we pack the curvature information into what we have right now? Yes?
The other two updates, if you go back, like if you go to the second update, so there was the original sort of Atom optimizer, and then you go to the second.
They're both the same thing.
There was, I think it was the Muon.
This is Muon.
Yeah. So that's the numerical linear algebra technique, right? That's just saying that if your GPUs are running into walls, right, we need to sort of change the way that they're oriented and make sure that
Yeah. But that one is specifically aimed towards solving the ill-conditioned matrix problem. Atom and Muon, the only difference is that specific orthonormalized step. They're pretty much doing similar things. They still have the momentum and they still have different learning rates and adaptive learning rates. They just have this one orthonormalized step because of this specific issue that we talked about.
And then if you go to Eon real quick.
Yeah.
So again, right, like that's another technique where if you look at power iteration, right, like power iteration is another technique that comes from numerical linear algebra. And it doesn't modify the original scheme as much as
Yeah. That was how I came about heard about Dion. That was my motivation. How can I pack more information into it? But yeah. Do we have any other questions?
How much faster is current Dion relative to like Dion and other sort of like schemes? I think you mentioned, for example, that Dion is faster than using LMW, but then do we see an increase in like a decrease in training time that's caused because we're having to send like less synchronization?
No, you see increase in training time because we don't have to wait as long, per se. a lot of the training time actually gets wasted on the waiting for the sync to happen. Computationally, it is the same as Dion. Because computationally, all it's doing is, it's just a fork in the road. You look at the threshold. If the threshold is below the value, then we don't need to sync. And all we're doing is we're running local Dion on all of the GPUs. And if the threshold is greater than the value, then we're running real Dion where we do sync every single step. Does that make sense? So computationally, we're not changing anything. This is the same speed as Dion, but we're reducing the time it takes for the syncs to happen. Does that make sense? Yes.
So do you have a percentage number on how much of the time is spent on syncing?
Oh, on how much of the time is spent specifically on syncing?
Like prior to Curva Dion versus.
So that depends on the different types of machines you have. So there's no specific like number that we can say, oh, it takes this amount of time. The idea is, for example, if you have different nodes that are across the world, they definitely have lower bandwidth connections. So that takes a lot longer, versus if you have one node here and one node here and they're connected by Ethernet cable, that takes some amount of time, but it's not that much. This just gives us the capability to actually go through and have two different data centers on two different sides of the world and still be able to do this. Yes.
So in terms of security then, since you're shipping like information from like, potentially coast to coast, is there a chance for like users to potentially like intercept data that's going back and forth, or is it secure when you're syncing between GPUs at all?
I don't know. But what are you going to do with the gradient information?
I mean, that's true. But I'm just curious because you're shipping information from just like data in general.
I'm not quite sure. I do know that there's some clusters that have different locations and you can talk between the clusters.
Right.
But I don't really know how the networks of that all works. I assume it's pretty secure.
Right, okay.
Yeah. Yes.
You mentioned that one parameter, like the tau parameter, that you don't really need 0.1 to 0.9 or something. For your next steps, are you planning on like figuring out like a better way to determine how to tune that, or?
Yeah. To some degree, I actually have no idea what I'm going to do next, but maybe.
Gotcha.
Yeah. I actually don't believe that we really need tuning for this.
Mhm. So you just picked like 0.1 or something.
You pick 0.9 because that does less
Okay.
syncs. But you just pick the one that does the least amount of syncs.
Mhm.
Originally, I had the idea of making this tau decay over time.
Yeah.
But we found out that most of the syncs that need to happen during the start of the training, because at the start it's the most noisy and various amounts of curvature and a lot going on. So we need most of these 1% of syncs at the start, and then at the end, there was a run on 160 million parameters where you needed some in the start, and then you didn't need any in the middle part of the training or near the end until the very, very end. Does that make sense? Until like convergence.
Gotcha.
Yes?
Do you think like, I mean, did you do gradient accumulation when you did this? Like, do you think the curvature estimate gets better as you do gradient accumulation?
So Dion has gradient accumulation in it.
Oh, okay.
It's the momentum right here. So that GFT is the gradient.
Well, I guess I meant like you take your, like you split your batch into like mini batches, right? And then you like sum your gradients so that you can fit bigger batches into like a single update step. Like not this gradient accumulation, like when you do multi-batch gradients and then you take them together. and
Like
you-
DDP. Like DDP, the thing we talked about at the very beginning. Are you talking about this distributed data?
Well, it's like synchronizing across GPUs, right?
Yeah, this is.
Even on a single GPU, you can take multiple batches and then add gradients later, right?
Yeah, so that's basically DDP. Single batch SGD, what you're talking about is the exact same as DDP. That's what makes it insanely beautiful and work. Does that make sense? Because if you think about it, I'm splitting the data between all of the GPUs and I'm combining it together like I were to do it in mini batch gradient descent, where I have different batches of data. I'm going through the gradients and then combining them together. Does that make sense?
Yes, I think so, yeah.
So Curva Dion is compatible with DDP and FSDP because Dion is compatible with DDP and FSDP. And FSDP again, is where you split the model parameters itself within the different within the different GPUs. Does that make sense?
Yeah, yeah.
Any other questions? Yes.
I don't know if you mentioned this before, but I think you briefly talked about how like using Curve beyond like the information that's lost is like mentionable. So how would you classify like mentionable in this case?
Negligible in the case that if I had different initializations, it would be the same for Dion versus Curve by Dion. Does that make sense? For example, if I had initialization A and initialization B, and I trained on Dion, the difference between those two is how much the difference is with the same initialization and Dion and Curve by Dion. Does that make sense? Which is statistically negligible in our case. Yeah? Any other questions? Yes?
Like also, as part of this research, have we seen like a decrease in like an ability to decrease model sizes because we've been able to like sort of I guess like reduce the number of redundant like parameters and training through like through that kind of like estimation that you said, where like, we're not going to the same like point. And then are we able to sort of say that now we can make more like performant models at smaller scales, or is there?
Well, Kimi was proof of that, and there's ongoing research on that specifically. And how do we pack the most amount of information in that, in the smallest model possible? It's actually a very big part of theoretical ML, and it's called feature learning. How do we define feature learning, and how can we learn the most amount of features with the smallest amount of neural networks? Does that make sense? Yes.
Just so I'm understanding it correctly. So the syncing part is basically preventing it from getting into a lower rank, right? And then losing some of the, or like sacrificing some of the computation.
The syncing part is preventing it from
From losing like ranks or like wasted neurons, right? Checking for that. Is that what syncing does?
Well, so at every single step, let's take DDP for example. At every single step, I have one model on all of the GPUs. I run it on different sharded batches of data, and then I sync all of our information in all of the models. So now, after everyone has gone through that one step, everyone has the same exact weight parameters. Does that make sense?
Oh, okay.
That's called syncing, where we match all of the weight parameters on all of the GPUs. Yes? Any other question? Yes.
Is communication a big problem when you do inference? Like, could you use this to reduce inference costs when you distribute it across a bunch of GPUs, or is that not a problem?
Well, this is just for training.
Yeah, but could you use it for inference? Like, if you're doing inference on multiple GPUs?
Well, I'm sure you can use curvature somehow. I don't know if RMMC is the exact metric you can use here, or anything related to this but there is intuition, and yeah, we can use curvature to kind of figure out where this goes, and figure out inference.
How about for like fine tuning?
Yeah, fine tuning is part of training, and this is like part of pre-training. So all of this can be used in fine tuning and all of that. We have not tested it on fine tuning, but we don't. I assume it works. Any other questions?
What evaluation methods do you use for Curve Dion to test its performance as the tau went down, to see if there's a difference in performance?
So for most of them, from 160 million parameters through 50 and 1.3 billion, we used just validation perplexity, which is the common standard. And for 3 billion, we tested at an actual evaluation metric called MMLU, and it performs the same as Dion would if we trained the full thing on Dion. Does that make sense?
Yeah.
All of the other models are too small to actually be coherent in a sense and be cool as an LLM. Yeah. Any other questions? All right, if there's one thing you guys take away from this entire presentation, is that optimization is a very, very cool field to be working in. And in fact, to make a lot of these trainings like LLMs possible, it is only with optimization that we can make it accessible to every single person out there. Because maybe there are companies or people who can't afford that much GPU for every hour of the day. but optimization makes things like this possible. So I would recommend all of you guys to look up any of the things we talked about today and try to see what are different holes that you can poke in different methods that you see in this or any other field that you're working in right now, and try to optimize it, because it's one hell of a journey. All right, thank you.